So, okay class. So, this is maybe the last part of the presentation and fuel and combustion. Okay, so this time we will now continue our discussion for the sample given. Okay, so this is another example. Okay, so a steam boiler burns fuel oil with 30% excess air and represented as C16H32. Okay. So the fuel gas leaves the preheater at 220 kilopascal. Find the actual air fuel ratio. Okay, so solution. So the fuel is CnHM or the hydrocarbon fuel, which is C16H32. Okay, so let us now determine the theoretical air required. So this is class the derived equation. So in our previous discussion in part 3. Okay, so this is 137.28 multiplied by the number of moles of carbon plus 0.25 of the number of moles of hydrogen over 12N plus M. Okay, so take note class that the numerator here is the air and the denominator is fuel. Okay? So substituting all the values, the theoretical air fuel required now is 137.28. The number of moles of carbon is 16 plus 0.25 multiplied by the number of moles of hydrogen, which is 32. So divided by 12 multiplied by 16 plus 32. Therefore, the theoretical air required now is 14.708. So this is in terms of kilogram of air per kilogram of fuel. Okay, so considering now the excess air given. Okay, so the actual air required now is, of course, the theoretical air multiplied by the excess air plus 1. Okay, so that is 14.708 multiplied by 1.3 is equals to 19.12 kilogram of air per kilogram of fuel. So again, so this is by formula. So this is maybe the easiest way in order to determine the theoretical air fuel ratio, and of course, if excess air is given, the actual air fuel ratio also is easily determined. Okay, so let us take another example class. Okay, so we have here, in burning a typical coal, the theoretical air fuel ratio was found to be 15 kilogram per kilogram. Theoretical, okay? So the approximate heating value of the coal in kilojoules per kilogram is, okay? So by formula, again, the theoretical air required is equals to 7.65 multiplied by the higher heating value divided by 10,000. Take note class that the unit here is in BTU per pounds. Okay, so substituting values now, the higher heating value, okay, be determined using the amount of the theoretical air multiplied by 10,000 divided by 7.65. Okay, so that is equivalent now to 19,607.84 BTU per pound. Okay, so changing now this heating value to SI, so that is equivalent to 45,613 kilojoules per kilogram. Okay, okay, so another. So let us take an example, so which is more complicated than the previous one. Okay? So the dry exhaust gas from oil engine has the following gravimetric analysis. Okay? So carbon dioxide is 21.6%, oxygen is 4.2%, and nitrogen is 74.2%. Specific gravity at constant pressure for each component of the exhaust gas in kilocalories. Okay, so the specific heat rather. So that is in kilocalories per kilogram degrees Celsius. Okay, so here is now. For carbon dioxide, that is 0.203. For oxygen is 0.219. And for nitrogen is 0.248. So here is now the problem. So calculate the specific gravity if the molecular weight of the air is 28.97 kilogram per kilogram mole. Okay? So take note that the given is the gravimetric analysis, okay, and the specific heat. Okay? So let us now take the solution of this. So first, we are going to convert the gravimetric to volumetric analysis. Okay? So by this time, so that is the gravimetric is here. We have here 0.216 for carbon dioxide, 0.412 for oxygen, and 0.74 for nitrogen. So in order to change this to volumetric analysis, we have to divide this by the molecular weight of the components, which is the carbon dioxide, oxygen, and nitrogen. So for carbon dioxide, we have to divide this 0.216 by 44. So because the molecular weight of carbon dioxide is 44. So for carbon, that is 12 plus oxygen 16 times 2 is 32 plus 12 is 44. So dividing this now, we have 0.004909. So for oxygen, that is 0.42 divided by 32, since the molecular weight of oxygen is 32. So oxygen is 16. So multiplied by 2 is 32. So the answer is 0.001312. And for nitrogen, that is 0.742 divided by 28. Because nitrogen is 14, multiplied by 2 is 28. Okay. So that is now equal to 0.026500. So summing up now this result, okay? So that is equivalent now to 0.032721. So that is moles per kilogram mole, okay? So getting now the molecular weight of the product of combustion. So that is equal now to 1 divided by 0.032721. So the molecular weight now is 30.56 kilogram per kilogram mole. Okay. Getting now the specific gravity. So that is the molecular weight, of course, of the product of combustion divided by the molecular weight of air. Okay. So therefore, the specific gravity now is 1.055. Take note, the specific gravity is a dimensionless parameter. Okay, so I think it is clear to everybody. Okay, okay, so another class, maybe this is the last example. Okay, a gaseous fuel mixture has a molal analysis. Okay, hydrogen is 14%. CH4 is, this is methane, so 3%. Carbon monoxide is 27%. Oxygen is 0.6%. And carbon dioxide is 4.5%. And nitrogen is 50.9%. Okay? So determine the air-fuel ratio for complete combustion on molal basis. Okay? So, solution. So, let us now determine the chemical reaction of this composition or those elements which are combustible. Okay? So, let us now, for hydrogen, So, it requires 0.070 or for 0.14 hydrogen, it requires 0.070 oxygen in order to yield 0.14 water vapor. Okay? So, in burning hydrogen, and then combining it with oxygen, of course, the product of combustion is H2O or the water vapor. Okay, so here, another, this methane, so that is 3%, so that is 0.03, multiplied by the amount of oxygen required, which is 0.060. So, the product now of combustion, since this is hydrocarbon, of course, is carbon dioxide and water vapor. So, the amount now of carbon dioxide and the product of combustion is 0.3, and for the water vapor, that is 0.06. Okay? So, let us now sum up the oxygen requirement. So, summing up, 0.070 plus 0.060 plus 0.135, the amount now is 0.265. Okay, so for the actual oxygen now, and the product of combustion, that is, of course, the amount of oxygen required, 0.265 minus the oxygen present in the gaseous fuel mixture. Okay? So, which is 0.006 or 0.6%. So, therefore, the oxygen now is equals to 0.259. Okay, 0.259. So, summing up now, so that is 2.59 plus. So, this is oxygen. So, in air, the composition, of course, of the air is 79% oxygen and or 21% oxygen and 79% nitrogen. So, 3.76% or meaning the amount of nitrogen in the product in air rather is 3.76 times the oxygen. So, therefore, the value now is 1.2328 moles of air per mole of fuel. Okay? So, that is now the molal air fuel ratio. Okay? 1.2328 moles of air per mole of fuel. Okay? So, we have another example. A volumetric analysis of gas mixture is as follows. Carbon dioxide 12%, oxygen 4%, nitrogen 80%, and carbon monoxide 4%. What is the percentage of carbon dioxide on mass basis? Okay. So, converting again the analysis to mass basis. So, that is 0.12 multiplied by 44. So, that is 5.28. So, 4%, we have 0.04 multiplied by the molecular weight, 1.28. Nitrogen of 80%, 0.8 multiplied by 28 is 22.96. Carbon monoxide of 4%, so 0.04 times 28. So, that is carbon is 12 and oxygen is 16. So, 12 plus 16 is 28. So, equals to 0.56. Okay. So, let us now determine the total mass of the product. So, summing up now, the result is equal to 30.08 kilogram. Okay? So, the percent now of the percent mass of the carbon dioxide is, of course, equals to 5.28 divided by, so that is CO2, 5.28 divided by 30.0, equivalent now to 17.55%. Okay? Thank you very much, class. Okay?